Hello, this is our last lesson in chapter 8, talking about or comparing functions: linear, which we know, quadratic, which we know, and that function that we skipped a while ago back in October or November, thinking that we would come back to it at the end of the year. The way things are going, I don't think we're coming back to it. So let me tell you a little bit about that skipped function, which was the exponential function. Its general form looks like f of x or y equals a times b to the x, where a is the number that represents the initial amount, b is the number that represents the growth factor if b is greater than 1, and it represents the decay factor if b is a number between 0 and 1. X, notice this time the variable is in the exponent, and that represents the time that elapses. The parent function in its most simplest form, that's what a parent function is, looks like y or f of x equals b to the x. If this is growth, then I start off very small, it grows exponentially. And if it decays, it starts off with a certain amount and then decays exponentially. This is a function that's in the news a lot right now because this represents the way bacteria grows. It represents the way viruses grow, think coronavirus. It represents in science the way populations grow, rabbits, vermin. And if I'm looking at the decay function, think of scientists who are using carbon-14 isotopes to date the length of time that something has lived, or time has passed since it was living. If we, to show you, these are dramatic functions. Do you remember your teacher back in 6th grade maybe saying, what happens if you have a penny and you double it every day? How long does it take for that to be $1 million? Do you remember seeing that? If you didn't, it really demonstrates the power of an exponential function. So if I'm going to use this, I would start off, I want to know what's it going to look like. So my penny, I'm starting with 1 cent, and it's going to double. So my growth factor is 2. And I don't know exactly how long, so my general form is going to look like 0.01 times 2 to the x. Now, where this is going to be, x is days. How many days do you think it would take? If you started with a penny the first day, and when the next day, first day, I'm going to multiply by 2, so now I have 2 cents. And then I'm going to double that, so now I'm going to have 4 cents, and then 8 cents, and then 16 cents. How long before you have $1 million? If you guessed 27 or 28 days, you are spot on. So see the power of that exponential equation. It's why your parents tell you maybe to invest your money, save your money while you're young, because it grows exponentially. And by the time you're ready to retire, you have a nice pot of money waiting for you. That's the theory. And it grows a lot faster than if you wait till you're old and start saving, and I can type it out. Look in your book. So now that we've seen that characteristic exponential curve, look in your book. This is on page 460, choosing functions with which to model data. So we know linear equations, y equals mx plus b, if I put it in point slope format. And we've got quadratic equations, y equals ax squared plus bx plus c. And now we have exponential equations, y equals a times b to the x. If we look at example 1, where you're using the graphs to represent a function, one easy way to tell what you're dealing with is just plot the points and see what they look like. And that's what they're showing you in example 1. They have parabolas, that characteristic U shape. Linear, of course, is that straight line. And now we know exponential functions have that smooth curve. Looks like sort of half a parabola. Notice in that exponential function, I forgot to tell you, or to point out, it has an asymptote. So if we talk about domain and range for that exponential function, the domain is all reals. But the range, I'm never going to go below whatever that bottom numbers. If it's the parent function, it never goes below the x-axis. So y would never be less than or equal to, never less than 0, or equal to 0 either, for that matter. So, three that we're looking at, we can plot them and see monitoring progress. If you plot those and you're curious, the first one should be linear. The second one, if you plot that, is exponential. I'm sorry, I was reading the example. If I'm looking at monitoring progress and you're plotting those points, the first one should be quadratic. The second one was exponential, and the third one was linear. You don't have to plot the points, however, in order to tell what's going on. So look at the core concept. This is the box at the top of 461. It's telling you if I look at the y values, there's a lot that I can tell about that function. The first thing we need to make sure, however, before we look at those y values, is that those x values are constantly evenly spaced. So there's a constant difference between the x values. If that's true, then we can look at the y values and see what's going on. So look in the core concept. If it's a linear function, the first differences are constant. That means if I'm looking at the distance between the y values, they always equal the same amount. Exponential function, the consecutive y values have the same ratio. That means if I divide them by each other, I would get the same number. And the quadratic function, the second differences are constant. And so, look at example 2 and see what this means. I've got a table of values, so there's an x and y. X's range from -3, -2, -1, 0, and +1. So the x values are evenly spaced. So that means we can look at those y values and see what's going on. The y values that they gave us were 11, 8, 5, 2, and -1. When I'm testing these, the first thing I would probably check for is this exponential? And the way that I would check is look at those y values. If I have 8 divided by 11, is that the same thing as 5 divided by 8? Or 2 divided by 5? No, not a common ratio. So these are not representative of an exponential function. The next thing to check are the distances between. So first differences, I'm subtracting. So 8 minus 11 is -3. 5 minus 8, -3. 2 minus 5 is -3. -1 minus 2 is -3. Those first differences, that's what we call that, are constant, and therefore this is a linear function. A word to the wise, when you encounter problems like this on your SAT, don't stop with the first two. Always make sure you're checking the last one or all of them, because they like to sometimes sneak in one that's not at the end that's different, and so that would throw your constant differences out. Always check all of them. So for that, this was example 2A, and we decided that it was linear because those first differences were constant. Example 2B, I think I started with the same, no I didn't, the same x values. It started with -2, -1, 0, 1, and 2. The y values that they put with that were 1, 2, 4, 8. Well, if I put them with the same numbers that they had, we would have the next slides. So 1, 2, 4, 8, and 16. And so I'm checking ratios, just 2 divided by 1. Is that the same thing as 4 over 2? 8 over 4, 2, 2, 2, and 16 over 8 is also 16 over 8 is also equal to 2. And so constant ratios, therefore this equation, example 2B, was exponential. The ratios of those y values, make sure you're checking the x. Those were 1 apart, evenly spaced, therefore we're good to check the y's. The y's are common rate, the ratios were constant, and therefore it was exponential. If I'm looking at example 3, or C in this one, where I have, again, an x and a y. X was -2, -1, 0, 1, and 2, and this time y was -1, -2, -1, +2, and 7, we might have a suspicion that this is quadratic just because look how symmetric. But if we weren't sure, we're going to check. So these are evenly spaced, so we can check the y's. If I looked at ratios, I would have -2 over -1, and -1 over -2, I have 2 over -1. Ratios aren't constant, so we know it's not exponential. And when I'm looking at it, -2 minus that -1 is -1 for that first difference. -1 minus that -2 is +1. 2 minus -1 is 3, and 7 minus 2 is 5, and definitely not constant. So check the second differences. So 1 minus that -1 is 2. 3 minus 1 is 2. 5 minus 3 is 2. The second differences are constant. Therefore, this was a quadratic function. As you get higher degree equations, it turns out that if their third finite differences were a constant, it's a cubic equation. If the fourth finite differences are constant, it's a quartic equation. The highest power would be 4. It's not bad to do these are not tedious, as tedious as it could be. If you're doing it for quadratic equations, when you come back, remind me that I'm going to show you how to do differences on your calculator. I don't want to try to do that on the video. We have issues even in the best of times when we're doing that. If you look at monitoring progress down at the bottom of that page, 461, and looking to see whether that's linear, exponential, or quadratic, take a minute, look at the x values. Are they evenly spaced? Yes, they are. So look at the y values. Check the common ratio. I usually do that first. Check the first differences. What did you find? 3 over 1, 9 divided by 3, 27 divided by 9, 81 divided by 27. Common ratio was all constant at 3, and therefore that was an example of an exponential function. Turn page and look at writing functions to model data. They gave us a chart. I wrote down, so these are so x over y. And the values that they gave us were 2, 4, 6, 8, and 10 for x. And when we look at that, are those x values evenly spaced? Yes, they are. They don't have to just be different by 1. So 2, 4, 6, 8, they're 2 apart. That's a constant difference. So we can do something with these y's. So I have 12, 0, -4, 0, and 12. That doesn't look like quadratic. I've got my low point, I'm coming up, but if that's true, then the second differences should be the same. So we're just going to double check just in case. So 0 minus 12 is -12, -4, 4, 12. First differences weren't the same. Well, let's check these. -4 minus that -12 is +8. And 4 minus that -4 is +8. And 12 minus 4 is +8. So our second differences are constant. Therefore, for part A, we know that we are writing a quadratic equation. The other thing we know when we're looking at our data points, what do I have? 4, 0, and 8, 0. Do I have x-intercepts? I hope that you see that we do. So I'm going to use those intercepts. Remember, those are the same thing as the zeros of a function. So I'm going to have y equals a, because I want the particular quadratic equation that's going through those two x-intercepts, those two zeros. And so we're going to write these in factored form, so x minus 4 and x minus 8. And then we want another point from the table because we've got these values, I need an x and a y. So I think the one your book picked was 2, 12. They went with the first point. That means that where I see y in my general equation, I'm going to replace it with the y value. So 12 equals a times, we're using this point, so the x coordinate of that point was 2. So 2 minus 4 and 2 minus 8. And then we see what we have. So 12 equals a times 2 minus 4 is negative 2. And 2 minus 8 is negative 6. And so when I multiply those together, I have 12a equals 12. And that means that a equals 1. So now I'm ready to put this back into my equation. So y equals, a was 1, so I didn't have to worry about it. X minus 4 times x minus 8. When I FOIL those, x squared minus 4x minus 8x is negative 12x. And negative 4 times negative 8 is positive 32. And from those points, we wrote the specific quadratic equation, the exact parabola that would produce those points if I looked at the x and y values. If you look further, the monitoring progress is asking you to create from that table of values an exponential function. I'm not asking you to do that. When we do this, it'll either be linear, probably not, or quadratic, probably so. So look at this example and know what to do. The last thing we want to talk about is rate of change. Remember when it was linear equations, the rate of change was constant, and we called it slope. But if you can picture a parabola in your mind or an exponential function in your mind, they don't have slope because they don't have a constant rate of change. So when we compare those, we use something called average rate of change, which is what they're showing you at the bottom of page 462. There's a exponential function, there's a parabola, parabolic function, quadratic function on the right, and they're picking in an interval. They chose, in this case, they chose A comma B and an A and B point. And they're just looking at the slope as if a straight line passed through that. And so the rate of change was the function at point B minus the value of that function at point A divided by B minus A. So it was like delta Y over delta X, a change in the Y values divided by a change in the X values. Looks like slope, right? Change, rise over run. I just picked two intervals and looked at the endpoints of that interval and calculated what the slope would be if there were a straight line between those 2 points. When you're looking at 463 up at the top, that core concept, the average rate of change of an increasing exponential function will eventually exceed that of an increasing quadratic. So exponentials grow. Hear that term, growing exponentially? Happens very quickly. Did we do the penny? Did you find out that it was 27 days? In 27 days, you would have $1 million? I can't remember if I don't have you here to ask. It's hard to remember what we did. I meant to do that. Did we talk about 0.01? Doubling it? I think we did that. To the X, and found out that if that was 26 or 27 days, you would have $1 million, how fast it grows. So exponentials will eventually exceed the rate of any quadratic equation. And any quadratic equation will also exceed the rate of change of any linear equation. And that's what that little core concept is telling you. The average rate of change of an increasing quadratic function eventually exceeds the slope of an increasing linear function. And then example 4, they were using a table of values to calculate, have a graph on the right, website B, and then a table of values to calculate the rate of change. And they chose 10 and 20 because they're easy to work with, and found that in the table, the average rate of change was 75. And in the graph, using that same interval, 10 and 20, and just calculating the values, looked like 95. So website B was growing faster in that first 25 days, or first 20 days. Then if I'm looking at part B, what it says, Okay, after the 20 days, who's going to be faster? Well, website A was growing. If you look at it, it's a linear function. And website B is either quadratic or exponential. So we know just from the shape of that curve that after 50 days, website B is going to have more members than the linear one. That is all I want to do with this lesson. Your homework that goes with this is from the textbook, no worksheets this time. It's 1 through 4, 6 through 28 even, 31, 36, 41, and 43 through 50. That's 1 through 4, 6 through 28 even, 31, 36, 41, 43 through 50. I don't know how long this is going to continue, but I miss seeing your faces when we're doing this. This is excruciatingly hard for your teacher to do. Hopefully see you soon in person, and if not, we'll continue with this. Email me with questions. You can call me at home, 410-603-5074. With questions, you can use the discussion block. Stay in touch. Miss you all. See you later.